Now we're going to talk about what we can say about when we can use equalizing strategies. And that's given by this equilibrium theorem. The theorem says if we have an m by n game with matrix A, an m by n matrix, and let's say the value is v, if p is an optimal strategy, this vector p, probability vector p, is an optimal strategy for player 1, and q is an optimal strategy for player 2. Again, I've always been writing these incorrectly. That should be q1 through qn. Then we can actually have equalizing strategies. I'm sorry, then these are equalizing strategies in the following sense. Not absolutely equalizing strategies, but they will be equalizing in the sense that the value of the game will always be exactly equal to this thing on the left. What is this on the left? Again, this is the expected return if player 2 is using the optimal strategy Q, and player 1 picks row I. So what does this say? It says that expected return when player 1 picks row I and player 2 uses the optimal strategy Q will be exactly, not just greater than or equal to the, I'm sorry, in this case we'd say not just less than or equal to the value V, but exactly the value V for all of, not for every possible row I, but at least for those row I's where P sub I is greater than 0. And that's a very important thing to understand. So we're in the situation where player 2 is playing an optimal strategy Q, player 1 is playing an optimal strategy P. Some of these might be zeros. In an optimal strategy, player 1 might just ignore some rows. Well, in those cases where player 1 ignores that row, we certainly can't make the claim that the expected return when player 1 plays that row will be equal to the value of the game. Maybe the expected return would be much worse for player 1, much better for player 2. But for every one of those strategies, individual strategies 1 through m, row 1 through row m, that player 1 plays with a positive probability in an optimal strategy, then you're going to get the exact same expected return, regardless of which one is played, as long as player 2 plays the optimal strategy Q. So that's what we mean here by for all I for which P sub I is positive. And the similar statement the other way around says that this quantity, which is the expected return if player 1 uses the optimal strategy P and player 2 plays column J. So that expected return when player 2 plays column J will be exactly the value of the game, not necessary for every choice of J, but at least for those choices of column J which have Q sub J greater than 0, meaning for all columns which appear in an optimal strategy for player 2 with some positive probability. A column which is absolutely terrible, totally dominated by other columns, in an optimal strategy might appear with probability 0, and you certainly wouldn't expect this quantity here on the left to equal the value of the game for such a column. But if player 2 plays any column which exists with a positive probability in his or her optimal strategies, then we have the expected return exactly equal to V. So why is this called the equilibrium theorem? It says we basically have equalizing these strategies, P and Q are basically equalizing, not for every choice of row and column, but for every choice of row where that row appears with a positive probability in player 1's optimal strategy, and every choice of column which appears with positive probability in player 2's optimal strategy. Now, that's an important principle, and the proof is in some sense almost a triviality. Why? We just argue by contradiction. Suppose there's some number k, and we'll think of this as row k, such that pk is positive, but this expected return for player 2 playing player 2's optimal strategy is somehow not equal to v. And since this expected return will always be less than or equal to v, that's one of the characteristics of an optimal strategy for player 2, that these things will always be less than or equal to v. If it's not equal to v, it has to be strictly less than v. And then we just write the value v, which we already saw was equal to this. Remember, whole thing is exactly the same as the sum from I equals 1 to m, the sum from j equals 1 to n of, we can write p sub I, aij, q sub j. This quantity here on the left, which is the same as this quantity here, is what you get when you add up over every entry of the matrix. That return, the value of the entry of that matrix times the probability that it occurs in this pair of optimal strategies. That probability is p sub I times q sub j. You add that up over all I and all j, and you do get the value of the game. So that's just this. I've written it this way because in this case, this quantity, the sum from j equals 1 to n of aij qj, we're assuming here is strictly less than the value v. And if that's the case, this whole thing is strictly less than, because of this sum from I equals 1 to m of p sub I, that's this part here, times v. This part here is strictly less than v, and that gives us that strict inequality there. But this quantity, of course, is equal to v, and that's just because the sum of p sub I, we've seen this before, is exactly 1. That just says that the vector p is a probability vector. And of course, this is impossible. This would be v less than v. And what does this contradiction tell us? It tells us that we can't have this situation where these are unequal. In other words, we must have the situation where these are equal. And remember, this was all when p sub k was positive. Where did this assumption that p sub k is positive come in? Well, to get this inequality here, we said that inequality comes from the fact that this is strictly less than v, but this is multiplied by p sub k. If p sub k were 0, that wouldn't matter, and that wouldn't get us that less than there. That part would be ignored. So it's important that p sub k, the thing that multiplies this when I equals k there, and that gives us this part here, that p sub k be non-zero in order to get this inequality we need to derive our contradiction. So this proves the first part of the equilibrium theorem. The second part is really proved in an identical way, just when you look at rows instead of columns. And now this equilibrium theorem leads to this thing we call the principle of indifference. It tells us, as one special case, if you have a matrix game where all strategies are active, what does all strategies active mean? That means, say, the probability vector p, which, say, for a 3x3, I'll talk about this for a 3x3 game, p1, p2, p3, all p sub I are strictly positive, I plus 1, 2, and 3. So all strategies active means in an optimal strategy for player 1, there's a positive probability for each and every row. And the same thing for player 2. Say q is q1, q2, q3, and then the q sub j is greater than 0 for j equals 1, 2, and 3. And so for player 2, all columns are active, meaning all columns appear with positive probability in an optimal strategy. So when there's an all strategies active game, then these optimal strategies are in fact equalizing strategies. Because since all probabilities are positive here, the equilibrium theorem tells us the expected return for each player, regardless of the other player's choice, will be exactly the value of the game v. Here's the difficulty in applying this principle of indifference. How can you tell if all strategies are active? It can be very tricky. In fact, that can be something you can't tell very easily in advance. Here's an example of a 3x3 matrix game. Player 1 picks the rows, player 2 picks the columns. What should they do? It's very hard to just look at it and tell exactly what's going on. One giveaway that at least we have a chance for all strategies to be active is that there's no saddle point, there's no column that's dominated by any other column or combination of columns. There's no row that's dominated by any other row or combination of rows. Each row in each column has some good choices and some bad choices. It looks like, at least, it either looks like it is an all strategies active game, or at least it very well might be. So let's pretend for a minute it is. And you'll see that's not a horrible assumption, because if it turns out we're wrong, we'll see that later in the computations. So let's act as if it is an all strategies active game. How would we find the optimal strategies? Well, we find them by just saying, let's look for equalizing strategies. We want to find this optimal strategy P for player 1 by making it an equalizing strategy. Well, what does that mean? For player 1, you have P1 is the probability for row 1, P2 is the probability for row 2, P3 is the probability for row 3, and we ask, what's the expected value, expected return, if player 2 plays column 1? Well, it would be -1 times P1 plus 6 times P3. And if we're going to have this all be an equalizing strategy, that should then equal the value of the game V, which we don't know, but that should be true if this is an all strategies active game, and we've already learned now the equilibrium theorem. What happens if player 1 plays this probability vector P and player 2 plays column 2? Well, then the expected return will be -2, here this -2, times P1 plus 5 times P2. So we'll want that to equal V. And similarly, for if player 2 plays column 3, we'll want 7P1 minus 3P2 to be V. Now I'm going to add one more equation, P1 plus P2 plus P3 equals 1. That just says P is a probability vector. And the reason I added that equation is because now we have a system of 4 equations and 4 unknowns. These are 4 linear equations and 4 unknowns, and in general we'll get a solution to that system. And this is a really messy 4x4 system. I think every one of you has learned in linear algebra how to solve this 4x4 system, a system of 4 equations and 4 unknowns. I'll tell you exactly how I solved it. I asked my computer algebra program to solve this system, but you could all do it by hand. And what does it tell me? It tells me there is a solution. The value of the game is exactly 174 139ths. The probability P1 is 48 139ths, P2 is 54 139ths, and P3 is 37 139ths. Now this tells us, you'll see these are all positive probabilities. This tells us, if this is an all strategies active game, that in fact here's the good optimal strategy and here's the value of the game. We have to make sure that player 2 has similarly an all strategies active optimal strategy. In other words, an optimal strategy with all probabilities positive. So player 2 plays column 1 with probability Q1, column 2 with Q2, column 3 with Q3. And so we're looking for this optimal strategy for player 2, the probability vector Q1, Q2, and Q3, that makes the expected return, regardless of which row player 1 picks, equal to the value of the game V. Here you see I've set up the equations that tell us the expected return if player 1 picks row 1. We set that equal to V. Player 1 picks row 2, row 3, each is set to V. And we add this equation that the sum Q1 plus Q2 plus Q3 equals 1. Since this has to be a probability vector, we get another 4x4 system of equations, 4 equations and 4 unknowns. And again, I had my computer algebra program here solve that, and we get exactly the same value, which is good, as well as the values Q1, Q2, and Q3. Notice they're all positive for player 2. What do we conclude? Well, we conclude that this really was an all strategies active game, because if player 1 plays the probability vector P that we saw in the previous slide, and if player 2 plays this probability vector Q with these values of Q, they each will get an expected return of V no matter what the other player does. That tells us again that V is the value of the game, and those really are in fact optimal strategies. So something that looked like it had all strategies active we tried to compute as if that were the case. We find that it is the case, since we get the corresponding probability vectors to be ones with all positive components, and we've solved the game entirely. Now, will this always work? No, it will always work if the game truly is an all strategies active game. We'll see in the future examples where it can be very tough to understand when this happens and when this doesn't, and see that in general, if you have games which are not all strategies active, it can again be quite a bit trickier than what you've seen here.